Good afternoon, everyone. On behalf of IEEE Vehicular Technology Society and UK and Ireland chapter, I warmly welcome you for today's lectures, and this is part of our ongoing VTS lecture series. I'm Dr. Riazul.islam from the University of Aberdeen, and I'm currently the chair of IEEE VTS UK and Ireland chapters. So I'm here to moderate this session. And as you know that this session is being recorded, and the recording will be made available through appropriate media channels. So members of the wider community, they can access it at a later time. And as usual, I also like to acknowledge and sincerely thank my colleagues from the chapters. Our vice chair, Dr. Tianjie, and also Dr. Ashraf Mahmud from the University of West Scotland for their continued supports, along with all our well-wishers to help make this event possible. And obviously, it's my great pleasure to introduce our today's resource person. This is Dr. Ferdian Jovan, who is currently an assistant professor of computing science at the University of Aberdeen, and his research expertise is mobile robotics and intelligent autonomous systems. So he held various research positions earlier, including leading UK universities, University of Bristol, University of Hull London, University of Oxford, and also University of Birmingham, from where he did his graduations. So today, he will, presents robotics under constraints, that is optimizing energy, perception, and intelligence at the edge. And if you have any questions, please hold it. We will have separate questions and answer sessions, which will follow after the talk. So with that, I will hand over the floor over to Dr. Fardi. Fardi, please go ahead.
Okay, thank you, Riaz, for this very warm welcome. And thank you everyone for attending this and for the opportunity. So for today's topic, we will explore the applications of machine learning and robotics and also edge devices. Basically, when kind of like we talk about machine learning, usually our minds as a computer scientist usually go directly to neural networks and deep learnings, which is true. And even in robotics, these deep learning models have been heavily adopted when it comes to kind of like computer vision and also deep reinforcement learning. But the problem is that these fancy techniques comes with a hefty requirement, like computational power, heavy computational power. So you need to have GPU and also high energy consumption, especially during training or perhaps like when you kind of run it continuously to do inference. So this is one of the reasons that many applications that use this fancy and high power required of deep learnings usually are adopted or tried in a simulated environments rather than the actual robots. If this is a problem for robotics or robots, then it becomes more problematic when it comes to edge devices and also wearables. So in this opportunity, I would like to show you that robotics, as well as edge devices, we can have other options as well that don't require heavy computations or energy extending. The point is that we want to extend the operating time of these robots or edge devices as long as we can so that they can do what they're supposed to do. At the end, I'm not against deep learning per se, and because it has its own advantage. So at the end, I will show that how we can approach the development of deep learning framework systematically, with the aim is to kind of optimize its performance when it is deployed in the actual hardware. So let's get started with that. Before we talk about the constraints and optimization problem, I would like to take this opportunity to kind of like clear up what this talk is actually about. It's all about resource-aware autonomous intelligence. These resources can be in the form of sensors, can be in the form of how it operates and how long we can extend the operating time, or also can be like capabilities that these robots or edge devices can do. So many of the research talks today are not something that can design in a lab and then deploy to the real world and expect everything works in. Sorry, how do? Yeah, sorry, I just hear the music from my side. So yeah. So many of these research are not something that you can design in a lab and then deploy in a real world situation and expect everything works as intended, because real world is chaotic. Many things are or can be cluttered and unstructured. And when it comes to the data itself, the data distribution as well can be completely different between the ones that you see or collect in the lab compared to the in the controlled environment compared to the one that you see in reality. So if you want to have models that work in real world, it is better to use and collect the data from where the models are gonna be deployed, being aware on the limitation of the hardware as well. So that's kind of like the main takeaways from this from my talk. Yeah. So my first topic is about surface robotics, where its job is to understand population level human activity. And yeah, so when you talk about like human activity, maybe we think about like, oh yeah, let's have a develop state of the art human activity recognitions. But there's no point on developing this kind of thing if it's designed in the lab where everything is controlled, because it will not work when it is deployed in real world. Yeah, maybe because like the person is too far away, or the person is not facing in the right way, or perhaps some of the parts of their body is occluded by something. So hopefully, I mean, these videos that I've been showing you kind of like help to convey my message. Okay. So yeah, the first talk is all about, or the first part is all about like what I did during my PhD, and the point is that it's not about maximizing the accuracy in detecting human activities or recognizing human activities. It's more kind of like on the data collection part. So we need to maximize uh, how this robot can have as much as possible human robot interaction, so that we can use that data, perhaps like to train the human activity models, recognition models as a downstream task. So the project itself, where my PhD was part of, was about developing intelligent mobile robots that are able to run for months in dynamic human environments without any intervention. So the robot is given a full autonomy to do its job, to understand its environment, and it is equipped with some basic capabilities to produce like 3D point clouds. These are human trajectories like this, to represent like how people occupy spaces over time, and some basic human activity recognition or people tracker. So you can think of this like the robot is like a child who knows little about its environment. So the first step is about to explore and learn, let's say like learn where the receptionist area is to be able to greet people in the morning and in the afternoon, learn where the emergency exit is so that it can guide people towards the exit when the fire happens, for example. So it needs also to learn about all the objects around. Maybe it doesn't need to know what the name of the objects is, but at least it should know like the shape and where it is. Definitely, it needs to learn about people behavior and how they occupy places, because the robot is deployed in human-centered environment. And my job itself was for the robot to have as many interactions with humans as possible during office hours. And this is
Pardew, I can't hear you. I don't know if there is any issue.
Yeah, we cannot hear. I think there is issue from there.
Can you please check?
Can you hear me now?
Yes, perfect.
Yes,
Ah,
you
okay.
can hear.
Oh, sorry. I was using a headphone, so to not to interrupt everybody here. So apologies for that. So should I continue or reset?
No, I think it was okay. So mostly maybe last 30 seconds we missed. So yeah,
Okay, cool.
it's not
No
a problem.
problem.
Yeah.
So yeah, let's just play it again. So yeah, my job here is during my PhD is for the robot to have as many interactions with the human as possible during office hours. And this is for kind of like data collection, where the data can be fed to train actual human activity recognition, the kind of like state of the art, or perhaps maybe to do online or continual learning with that as well. So this means that the robot needs to be in the right place at the right time, most of the time, to have this interaction, yeah, to maximize the interactions. So how do we do that? Yeah, let's assume that the robots are given a map with the boundaries like this, yeah, on the right-hand side here. And we are given like a set of decent tracker algorithm, whereby like upper body and lap detection combined together to track people. And as you know, that robot is not omnipresent, so it can only capture whatever is in front of it. So what that means is that the data that you will have will look something like a snapshot or a clip over time from various places at various time. Yeah. So that means that the robot doesn't have a full picture of every places. So what the robot needs in this case is that it needs to have a plan, yeah, or schedule basically to kind of like maximize or optimize the room or places that it needs to visit at the right place to maximize the interaction. And the tool that we can use is just a simple counting processes or puzzle processes here. And definitely by counting like interaction that the robots has during its interaction, you can use that to later on use that to visit the place, the same place again later time, or maybe the same time in different day to have that interaction. So this basically we collect the data to have the history, so basically to visit the place again. Definitely at the very beginning, this kind of robot will randomly just patrol around, go to any place, but after a couple of days, definitely it will gather enough information, like this graph here, so to know like kind of like the distribution of people occupancy over time in various places. But even though, let's say that you have robot knows roughly the distribution of people at certain part of the day, let's say, yeah, in the morning, people tend to come to be in the corridor, entrance corridors in the morning, and also in the afternoon when they leave. When you kind of like zoom on the data that's collected by the robot, you will see something like this, kind of like a jaggy, and some parts are missing, some parts are jumping all over the place. So you cannot really use this directly for the robot to kind of like have the robot visiting the same place again, to have use this as kind of like the schedule for the robot to visit this place. Because yeah, definitely you have like a missing data there, or like let's say 1 minute you expect to see like 10 people maybe in the kitchen. The next minute it's just like nothing. It's not because people just disappear, it's just the robot probably disappear or move on from that place. Yeah, so you cannot really say that how many people are there. So yeah, that's kind of like the missing data. So I solved this problem of kind of like jaggy and missing information utilizing the regularity or periodicity of human activities using Fourier transform here. We know that human activities are bound by regularity or periodicity, right? So if you, let's say you work in an office, you probably come at 9 a.m. in the morning, and then you leave around 4 to 5 p.m. in the afternoon. So in the, let's say in the entrance corridor or entrance area, you will see a lot of kind of like spike during that time, twice a day. Or maybe like in the kitchen during lunch hour, you will see a lot of spikes or activity, people doing maybe reheating their food or maybe making coffee, stuff like that. So there's like a very strong regularity in human-centered environments where people do things. So that's why don't we just use the Fourier transform, kind of like the point of this, like to transform the data from time series to kind of like frequency domain to find the actual frequency or the prominent frequency for each room. Yeah. So basically we transform our data time series from the time domain to the frequency domain. And I basically just devise a strategy to choose kind of like the K most prominent frequency along with its amplitude and use that to represent the place, kind of like this room signature now. And from there, I just reconstruct back this kind of like the filtered frequency from the frequency domain back to the time domain like this. So now instead of having this jaggy information like here, you have more kind of like smooth and non-missing transition. Yeah. So with this, then you can use that to start to use this information to plan the schedule or create a schedule. And actually, with this information as well, because we have kind of like room signature for each room, we can use that also this room signature from the frequency domain as features. And because we hypothesize that like the kind of like similar rooms will have the same characteristic in terms of prominent frequencies. And we test that with just like a simple clustering algorithm here to get the kind of like the, so as you can see here, we have the real office plan here, and we have the cluster office plan based on the features from the frequency. So why do we need this? Actually, in a way that robot learns the function of each room semantically similar to how people occupy the space. So it can differentiate between an open plan where you will see a lot of people there almost all the time during office hours. And it can differentiate meeting rooms where you will see people sporadically occupy them from time to time. And we use this information, the similarity between places, to decide which place worth visiting. For example, let's say that we want to visit room number 9 here, the meeting room. It is scheduled to be visited for robots to see. But apparently the door is closed, the robot cannot go in. So instead of like say that, hey, yeah, the door is closed, my job is done, so I'm just idling here. So it's better to kind of like for the robot to think, hey, what is the other room or other place that I can visit that has similar characteristics so that I can maximize my time, I can maximize the human interaction that I might see in that place. So that kind of thinking is what we need here. So it doesn't waste its time and also effort, especially that since the duration, because we have the schedule, the duration is already allocated for kind of like that time, maybe 15 minutes or 20 minutes just to visit that place. Otherwise, the robot will just like standing around doing nothing. So it's kind of like waste its precious energy. Okay, so we got the counting right. We got some kind of idea how we will schedule the visit for every place. Then, so how do we create this schedule itself? Yeah, so that the robot can maximize its interaction. So if let's say that we have the characteristic of the room like this for this room, yeah, all of this. When it's like they are kind of like compare this and this one, so you can see that this is definitely you want to visit, or the robot wants to visit this place at this time because it has a lot of people from historically speaking. But how about when we have like two kind of like similar number of people there? So which one, like for example, this, yeah, for between this and this, between maybe the open plan and the corridor, for example, maybe. So which one do we need to choose? So actually the counting that we did here to get this is actually not just like the simple counting. This is actually the parameter of Poisson distribution, which is the mean. Yeah. So each of these time series data here represented by the blue is actually the Poisson parameter lambda. And because this is a distribution, you can expect that there is like a variance number. The kind of distribution is not a point estimate, so we use that the variance informations to create an upper bound. It's also lower bound, but yeah, we only use the upper bound. In this case, the upper bound is represented by the red line here. It's like 95% of the credible interval. And yeah, so in this case, we use this red line to choose which one we want to visit. Yeah, I mean, if it's really close, then it's kind of like a random. But this is the place where we can like use the distribution together with Bayesian theory in using kind of like exploration method in this case. So it's simply basically, yeah, we use the red line, but the concept is very simple here is that, let's say that the place hasn't been visited at all, yeah. So the distance between the red line here and the Poisson parameter lambda will be high, yeah. So that means that, yeah, the place, it's kind of like the robot is expecting to see this number of people at the higher end of the spectrum. Yeah, so the robot might see that that many people there, might not see that many people there. So it's kind of like a speculation. So you can think of that like it's an exploitation strategy. Whereas as the more the robot visited this place at that particular time, the distance between the red line and the blue line will kind of compress. Yeah, so the variance is getting shrunk to the so that they are kind of close to each other. At this point, when you choose the red line here, or the red point here, it means that the robot already knows from the history that it will see this many people in this place. Yeah, so this is where the exploitation part comes into play. Yeah, so basically just a simple, you just use the red line to choose the place, and you might see a lot of people, or you will see, or you're going to see a lot of people. Yeah, that's kind of like the exploration trade-off using this strategy. So in general, basically this is kind of like the whole framework concept. I didn't talk about this part. So the part that we have been talking about is around this part. Yeah, so you have the Poisson process from the counting to create the schedule. And this schedule actually is not limited to kind of like the input from maybe a tracker or something like that. It can also be the task, yeah, the task that is given to the robot by people in the office. Maybe the receptionist asked to kind of like relay the message to a certain place, or maybe to the boss. So this kind of like task can come sporadically throughout the day, and you can model that as, again, as a counting problem. And the point of this is that when the task or the expected number of tasks is lower, you probably want the robot to kind of like schedule itself to charge its battery through during the day. Yeah. So let's say when there's no kind of like any place worth visiting or doing. So yeah, I mean, the input is not limited to tracker. It can be also used to anything that is related to counting. For the part, the early part here, where I combine multiple detector, you can find it in the paper here that I attach the detail. And then, yeah, so this is kind of like on the left hand side, you can see how the kind of like the scheduling plan produced by my framework. And again, maybe for those who wonder why I did not use any kind of like fancy technique for this optimization problem, hopefully this right hand side can give you some kind of reasons why, or excuse why I don't use any fancy techniques. So back then, this is a work that is done from 2014 to 18 back then, the kind of like the state-of-the-art optimization problem that can create the scheduling like this is done or was proposed by person David Duvenaut and also Zubin Garamani, people from Cambridge. They are professors now, and it is based on Gaussian processes. So still similar probabilistic machine learning. Unlike the Fourier transform, where you kind of like decompose time series data into frequency domain, Gaussian process that they develop can do that as well automatically. Decompose time series data into its suitable covariance kernels, because when you talk about Gaussian process, we need to talk about the kernels, and it can be like maybe white noise kernels, square exponentials, and also periodic kernels, which is I'm comparing here, yeah. But if you look at kind of like the reconstruction time from the kind of like JAGI data, original data to time series data to the kind of like the smoothing filtering part for this Gaussian process, it takes more than 2 hours. Yeah, just to reconstruct the data. I mean, it is fine to kind of like create schedule. So you do that. Maybe the robot can do that in the middle of the night where it's charging. So it's not a big deal. But the problem is that if you want to do this reconstruction during the day, to have like kind of like updated all the time, then it will take the power of the robots kind of like will be used to run this, yeah, to do reconstruction time. So that means it's affected the operating time of the robot itself, yeah. Whereas if you use my technique, it only takes 1 second, yeah. So it's a amplitude, yeah, 10,000 or 1,000 probably times faster than this one. And if, yeah, what that this means that, let's say if you run this during the day, the robot, I mean, can run or continuously. Practically, our robot can run for 10 hours. So if it starts from 7 a.m., needs to be recharged around 5 p.m. But if you run this kind of like GP Gaussian process, state of the art, to do this reconstruction and then scheduling, then it will take the time of that, yeah, operating time definitely. Then it means that the robot will probably lose a couple of hours just to recharge. So it will reduce at the end is that the interaction human basically not doing its job, yeah. So it's not good. And even if we compare in terms of the interaction that the robot can have, compared between the state-of-the-art Gaussian process with my own, it's kind of like similar, and even in some cases, it's actually beaten by my techniques. So yeah, so it's what I'm trying to say here is that, yeah, you don't need to go with a fancy thing. You need to look at the problem and try to solve it in its own problem, yeah, its own territory or domain. So you don't need to go with the kind of fancy technique as well. Just the problem, look at the problem and try to solve from there. Okay. So now let's move on the optimization problem in terms of like task completion for multi-robots, kind of, yeah, a bit similar to the previous one, but yeah, now it involves like multiple robots. And in this case, the project is rather simple. You can see from the video here, it explains what it means. So basically, you have like multiple robots like drones, autonomous boats, and also crawlers. The job is for these robots to work together in completing operation and maintenance tasks of offshore wind farms. Tasks like checking if there is like a crack in the wind blade, or how severe the effect of lightning strikes on the wind turbine, stuff like that. Yeah. So our job is basically to develop a planner that can coordinate all of this, so that these robots can work together to complete as many jobs or tasks as possible in one trip. Yeah, because I mean the cost for the robot to go there to the offshore wind farm and do things can be very expensive. So maximizing what they can do while they're on the site is crucial. And then, yeah, I mean, it's possible that in this case we can use deep learning, like maybe deep reinforcement learning, for example, or maybe LLM and combined with agentic AI. But not really. The problem is not because of the computation power or energy consumption. Now it's more kind of like the on the generated plan that these methods is producing. Yeah. So the policy that usually generated by DRL or deep reinforcement learning works more kind of like a joint probability distribution over the pair of state and actions, right? So if you have like a plan, the plan is a series of actions. So it's the uncertainty for long term plans gets higher and higher as you have more and more actions that you plan. Yeah, so it's getting uncertain and more uncertain. And not only that, when something goes wrong due to the black box nature of this DRL, it's difficult to trace back what causes that. So in this case, we use classical AI planning that can handle unstructured, structure constraint heavy problems to produce validated executable plans that are also interpretable so that when something goes wrong, it can be explained. So yeah, the extra problems here are clear, yeah, about the coordination and the battery capacity, especially for the drones and also the crawler. And the other part that we need to deal with is how we can accurately represent the world state or even like the robot state as well in the domain, yeah. So solving the coordination problem with AI planning is kind of like rather easy. You basically just need to have a discussion with the operators or technicians, the pilot that operates all those robots to get like to capture all the capability and state information for each of these robots, yeah, physically or like, yeah, logically as well. And then you present this problem as kind of like a PDDL domain, yeah. So we are using a PDDL here to do that. And then let's say that when you have a pilot or operator that wants to use this, they will create a task and using this interface to create a task or to create like a plan or mission. Then you just need to translate this into use all of these robots, yeah. Then you just need to yes, the environment. This is simulation, and then you have the real world. So you just need to create like the correct PDDL domain as well as the PDDL problem file, yeah. So there's nothing novel here. Just make sure that all the sensor information and the state of the robot, each robot is captured, yeah. So information about the wind speed, humidity, GPS location, as well as kind of like remaining battery capacity as well is captured and also represented in the domain and problem files. So this information is important to make sure that it's updated regularly and internally to ensure that the world state is accurately represented here. So one thing that we added as kind of part of the novelty is that we add the small monitoring systems for each sensor or actuator here that can feedback the progress and the status of the sensor. And this monitoring system is set on each robot called the feedback control system. So it can report dynamically when any unexpected changes happening during the execution of the action or during the operation time. For example, let's say that we talk about the actuator, yeah, the deployment actuator to drop the crawler from the drone. So if the actuator fails to open, this monitoring system will report back to the planner system, so to report that it fails to execute the deployment action. Yeah, so And because of the nature of the classical AI planning, is actually without like this informing this that AI planning will have like expected state. Yeah. So the expected state looks like this, that the end of the action, it will do kind of like the touch the robot, and then it, yeah, remove the information about the attachment. So with this, now that you can, with the feedback control, now you can inform the state arbitration or the kind of like the monitoring system that it's failing. So that this monitoring system now can kind of like delete or negate whatever happens here. Yeah. By kind of like adding back the attachment and delete the detachment information or state, yeah, to the state, yeah, of the internal planning. Then after that, then it can try to replan, yeah, and then patch this plan again to kind of like to be executed back by the robot. Yes, basically to kind of like redeem the failures there. Another thing that we need here is to monitor. We need to monitor and refine is the intangible state of the robot, yeah, of the world state as well. That might depend on the environment and the condition of the robot itself, yeah. So here I'm talking about like the duration needed to complete the action, the battery or fuel consumption, let's say per hour, and also the success rate of each action that has the embedded monitoring system that we just talked in the previous slide. Yeah. So we need to monitor that. We need to represent that in our domain as well. Yeah, that is needs to be tracked as well. So typically in a kind of like a standard classical AI planner, this information, like action duration or consumption rate and also success rate is generated at the very beginning as part of the state information that is put in the problem file, where the actual value itself is kind of like defined by the expert's opinion, yeah, or the pilot's persons like that. And this value basically will stay static forever, yeah, regardless of any changes happening in the robot or the environment, perhaps like in the future. For example, yeah, let's say that the pilot says that, oh, okay, the robot can fly for 10 hours. Nah, not realistic. So 30 minutes, can fly for 30 minutes, yeah. With this kind of like set of equipment, yeah. And then 6 months later, we want to add like maybe a new LiDAR sensor to that, that we will use to scan the blade of wind turbine. So you add that to the drone. So that is also increase the overall weight of the drone. So that also affects how long it can fly, or its operating time definitely will reduce. So yeah, stuff like that. The other possibly is also the environment. Let's say that, yeah, the weather can get very windy or very gutsy, maybe during autumn times. So that also affects the flying time of the drone in completing actions, meaning that this also requires more energy, meaning that it also has lower operating time. Yeah. So yeah, this kind of information, you need to kind of like update that, or a robot needs to kind of like have that updated from time to time. You can, I mean, ask experts or like computer scientists to kind of like modify the domain, but that's not fun. So it's how about we just use the capability of the drone itself to monitor the data inside and the collected data to have an adaptive system that can update this automatically. Yeah. So yeah, at the end is that we basically want to minimize the number of pre-planning and also failure, yeah, through this. Because again, yeah, the costs can be catastrophic. So we want to maximize the number of actions and without failure or without replanning. Oops. So here we propose kind of like to add a data-driven probabilistic model to track the changes on some of this critical information. Yeah, back again to battery consumption, action duration, and also the action success rate. So this adaptive system will have its initial value dictated by the experts, still the same, yeah. But the value is constantly updated via the information that you get directly from the agent's internal information or to the sensors when the related actions has been performed or was being executed, yeah. So you get the information from that. So for example, here, like we have the deploy crawler robot having the information. Yeah, so let's just move on to this. So maybe it's easier with this example. Yeah, so basically, yeah, the concept that I'm using here is kind of like similar to the one that I employed in the mobile service robotic research previously. So with probability distribution and also Bayesian filter here. So in case the concept is a bit fuzzy to you when I first introduced that, so I have a good example here. Hopefully it can help you understand how this data-driven probabilistic model works better. So instead, like having a point to represent data, yeah, we definitely now again represent everything in terms of distribution. For the action duration and also battery consumption or fuel consumption, we use Gaussian distribution here. And for the action success rate, we use Bernoulli distribution. So in this example, let's just use the action duration. So yeah, it looks like this. So we store this parameter of the distribution, which is Gaussian. So yeah, you need to have the mean and also standard deviations. That's the parameters. Those two parameters are for the Gaussian distribution. So you store that in your domain file, yeah, domain.pddl. It's kind of like the prior distribution here. And then, so now let's assume that we have we execute an action to deploy the crawling robot, yeah. So the action is like this, yeah, in PDDL format. So then after you execute that once, you will get some kind of data, yeah, how long it takes to execute that. So because the data is just one sample, and we just transform it into a distribution with the data sample as the mean, and we just fix the standard distribution, yeah. So it looks like this. So now, so we have the red line as the likelihood distribution coming from the sample data, and our prior distribution with green coming from let's say from the expert, yeah. And then using this together, using a Bayesian filter in combination with conjugate prior, you will have you don't need to do any fancy calculations. So this is kind of like a closed form equations that you can do automatically. Yeah, with conjugate priors to get this a new kind of like estimate of a new distribution or posterior distribution. So using this information, now you basically update the distribution that is stored in the PDDL domain file, and then use that information now to kind of like update like the duration, action duration, yeah. We use in this case not the point, but kind of like the minimum duration it takes to do this action, and also the maximum duration, possible expected duration with this, yeah, from the distribution. So this is what you give to the action definition of the action, yeah, in the PDDL domain. So yeah, one good thing from here is that we now our planner can adapt to different environment and configuration without the need of experts input anymore. Once we have the input from the very beginning, then you just use this to kind of like update the state of the robot over time. And it will be accurate. And definitely you need to kind of like to collect the data for kind of like each action or each action or for the battery information as well. You need to collect some data to get more kind of like accurate distribution, posterior distribution. But from our case, in our test, we test that with only 5 kind of like trials for each action. It's enough as kind of like the training data for this year to have a better estimate. And then I have been talking about kind of like the success rate. The success rate here is also taken into account to calculate the maximum expected action duration. So just in case like maybe like for example the actuator fails when it tries to open to drop the crawler to the wind blade, for example. So this kind of like action duration, why we kind of track it down or track it over time, is just to influence the maximum expected duration for that action. So you can have like some kind of leeway when something fails, without kind of like replanning everything when it fails, if that makes sense. So by doing this, you kind of like optimize the number of task completion for each trip. And and on the bottom here, you can see that how the general plan is basically removing any redundancy of and also unnecessary actions. So all the generated plan is clean, and the expected or like the actual things that happen similar to what is planned. So we basically reduce the number of repetitions or replanning, and also the number of failures. So that's pretty much for that. Again, we don't use any fancy deep learning for that. But now we are kind of like on the last part of this optimization problem. Now we've kind of like ventured to the deep learning and how we can make deep learning models that are efficient, both in terms of the size and the computation, without sacrificing much of the performance. So the goal here is to have like a deep learning framework that can be imported to a wearable and trained. The idea is that to be trained also in there with as little data as possible. So the framework will then be used to continuously track digital biomarkers tailored to specific individuals living with Parkinson's disease. So let me briefly talk about this project. It's called Sphere. It's from developed by University of Bristol, where I was there as a senior research fellow. A sphere is basically just a house filled with sensors from cameras, wearables, appliances sensors, ambient sensors, and also passive infrared technology, and that all developed in-house by engineer from University of Bristol. And the sub project that I was part of is we use this smart house to help elderly people living with neurodegenerative disease like Parkinson's identify their digital biomarkers that can be used to monitor wearing off effect of their daily medication. Because in case you don't know, that people living with Parkinson's disease, they need to take medication daily, to ease off their disease and also slow down the progression of their disease. So once we want to monitor that, because once the effect of the medication wears off, then their disease gets worse. I mean, the effect it's kind of like affecting their daily activities. So if we can establish like a baseline from their personal digital biomarkers, and to see how their kind of like typical biomarkers look like, then we can identify as like this is on, and then when they're off medication or they forget to take the medication, looking at these digital biomarkers, we can alert them
to remind them to take their medication. We can also use this to kind of like check the effectiveness of a new medicine, yeah, just to check whether the new medicine is more effective than the ones that they are taking at the moment, or their usual medicines, yeah. So to do this, basically we cannot use like robots anymore. Definitely we need to have like continuous and constant data collected for the deep learning to learn from. And this is the advantage of smart house over surface robotic, because you can collect data continuously, yeah, especially in the house. But you need to still be a bit worried about or aware about the personal space, and also yeah, data privacy and stuff like that, because we don't want to violate their personal privacy, like installing a camera in their bedroom and their bathroom, yeah. So definitely in this case, we need to maximize the utilizations of unobtrusive sensors such as wearables to continuously collect the data, yeah, while kind of like richer data coming from cameras can be placed in strategic places like in the kitchen, living room, stuff, places like that. So our target here is clear. We need to use these unobtrusive sensors to collect continuous data that can be used to detect whether Parkinson's medication is still working or it has started to wear off. And the problem here is that the data that comes from this is noisy, yeah, but the noisy is dependent on the severity of the person's disease, yeah, Parkinson's disease. And also the other problem is that how we can make this deep learning framework as small as possible, yeah, in terms of data and also storage. So storage efficient, data efficient. Again, the point is that we want to put this in the, oops, we want to put the sensors in the, we want to put the deep learning models in the sensors or wearables, yeah. So the only option here we have is that there are two options here that we can monitor. Either we monitor the continuous activity recognition using the accelerometer data or gyroscope and the gyroscope data, or continuous monitoring the location of this person using signal strength, RSSI, and also accelerometer. Because we don't have gyroscope, because gyroscope takes too much energy, so this in-house wearable can only last for 1 day. So they need to be recharged every day, which is not good. So we are left with the second option, just continuously monitor the location of the person using RSSI and accelerometer. And yeah, to make it simple here is that we only perform like room level indoor localization. So we don't care about like the exact position of this person. We just want to know where the person is, yeah, whether it's in the living room, kitchen, or yeah, in the bathroom or in the bedroom, yeah, stuff like that. So yeah, so why do we use this signal strength, yeah? So wearable worn by a person will receive signal coming from multiple access points, as shown in this picture, yeah, access points. So if you kind of like monitor this signal strength, yeah, the closer the wearable is to the access point, the higher the signal is, yeah. So every room, because we have like multiple access points, so every room will have its own kind of like unique fingerprints of this signal strength from every access points, and we can use that to kind of like create room classification. It's basically room classification, yeah, to do room classification. And then yeah, there's no privacy issue with this because we don't use camera. Camera is just used to kind of like get like ground truth for the labels, yeah. And we use the accelerometer data here to provide kind of like unique signals specific to certain rooms, yeah. For example, if you're kind of like in the corridor, typically you will walk there, yeah, with your wrist on your side, yeah, as shown in this signal here. on the top part. While when you are kind of like in the living room, you will probably sit, maybe watching television or reading a book, which has a different signal movement or hand movement than when you're walking. So yeah, using this information, you kind of like can help these accelerometer signals can help differentiate different rooms by kind of like associating to different activities in a way. Yeah. So especially this is important when kind of like the person is on transition or like is kind of like in the boundaries of the region of the area. Yeah, maybe between corridor and the kitchen, for example. So this helps, yeah, to kind of like identify that. But the problem, so yeah. Yes, forgot to tell you that, yeah, in this case, we have the data that we collect is coming from two persons. So they, in this house, there are 2 persons living, the person with Parkinson disease and also their carer acts as kind of like healthy control. Yeah. So here we have 2 kind of like 2 persons living for 5 days in this house. So using these 2 modalities, we were attempting to estimate the location of a person wearing the wearables inside a smart house. The problem here is that the accelerometer can get very noisy due to the fluctuated tremor symptoms that may occur randomly on a person with Parkinson. Yeah, so this can make like a accelerometer signals pattern, let's say for walking, similar to looks like it's happening. Yeah, when the person is basically just sitting in front of the TV in the living room, yeah, because of the tremor of their disease, yeah. And not only that, the severity of their disease affects the noise level produced by the accelerometer. So it's not just like noise, but it's more kind of like noise specific to the person, yeah, because the severity of the disease progress as they have the disease over time. So how do we solve this problem? So it's yeah, we basically cannot treat the accelerometer signals as the equal as the RSSI. So RSSI is more reliable. So we treat the accelerometer signals as an extra modality. Yeah. So just like a helper modality when things are kind of like normal. Yeah. So we need the network, the neural network to learn what normal accelerometer looks like. Normal here as in kind of like the person with PD is on medications, so everything's kind of smooth. Yeah, so let the network make a connection what the RSSI looks like with the normal accelerometer looks like for that area. Yeah, so we do this so that the network notice when abnormality happens. Yeah, maybe when the person forget to take their medication, so that it will not use the accelerometer data, yeah, or accelerometer information. So when that happens, the worst case, you will have the RSSI as a single modality to decide or to do the classification, room classification. The best scenario, you will have accelerometer to help RSSI to do the classification. Yeah, that's kind of like the novelty what we do here. Do we still have time? I think it's already 4 o'clock. I think you're muted.
Yeah, so we are running out of the time. So if you
Okay.
can quickly,
Okay,
yeah.
sure. So yeah, yeah, in terms of kind of like the results, we show that it's in general it's good, yeah. And the other thing that we want to focus here is that what if we kind of like reduce the number of training data that we have as small or as little as possible, yeah. So the training data, why is that? Because this is from one house, yeah. The data that you collect is coming from one house. What if you want to deploy this the whole system into a new house with a new layout of access points, yeah? You cannot fine tune that in the new place. So what you need to do is that you need to collect new data from that place. And it will be good if you collect the data coming from the person who will wear the wearable. Yeah, because remember, people with Parkinson's disease, the accelerometer can go crazy. Yeah. So you don't want to bother these people, participants, to wear the wearables and collect the data for hours for each room. Yeah. So that's why we kind of like go an extreme, like what's the effect if we just have like 4 minutes worth of data, training data to train deep learning model. Yeah, and this is how it looks like. And from this basically is that we use that to use to track the persons when they are kind of like on the key on the hub, or sorry, on the corridor. So the digital biomarkers that we produce here is the room-to-room transition duration. Yeah. So we use the hub as or the corridor as the hub to detect or to track this. Yeah. Their movement in the corridor, how long it takes for them to move. Yeah. As you can see from the top left here, when they are kind of like, this is all the PD people. Yeah. Parkinson disease people. When they are on medication, they look okay, they move rather fast, but when they're off medication, the severity of their disease shows. Yeah, so when they're kind of like on early years of their Parkinson disease, it's probably kind of like similar, but when they're kind of like yeah, maybe 10 years having the Parkinson disease, you can see. Yeah, so off medication can be seen here by just like looking at the transition duration. Yeah, how they move. Yeah, the slower they move, the longer it takes for them to move from one place to another. So we use that to track. Yeah, we use that as the digital biomarkers, and we show that our model is kind of like, yeah, can track pretty much okay. Yeah. And I just want to kind of like point out here is that because we use the Hall as the requirement is that we use the Hall to track the movement based on the output from the model, and it must be continuous. Yeah, so if it's like detecting Hall, then we can use that. Oh, this is like the person is moving at the moment, and use that as kind of like room-to-room transition duration. But the problem is that when we have the not enough training data, like only 4 minutes worth of the training data, for example, random forest basically fails to classify continuously, let's say for 10 seconds of the persons walking in the corridors, where basically that's kind of like the main point of to get this room-to-room transition duration. Yeah. So yeah, basically it's kind of like to the point that is rather difficult when you have like not enough data, or like creating a data efficient deep learning model. And it will get worse when you want to put that in the wearables. Yeah, so yeah, basically we kind of like just test on the kind of like room level classification problem for this, and we use the model that we developed and compare that with state-of-the-art LSTM, or kind of like the replacement of LSTM, Mamba, or state space, based on state space structure model. And we just basically show that, yeah, kind of like it works. But again, if we want to use this to kind of like track the room, to track room-to-room, to get the room-to-room transition duration as kind of like digital biomarker, we're not there yet, and we're still struggling to kind of like compact, at the same time make the model as data efficient. Yeah, so that's, I guess, pretty much it from me. I think you're muted. Yes, I think you're still muted.
So thank you for the sorry for that. It's really very fascinating and thought-provoking lectures, I would say, especially 3 lectures are combined into one, and it's really great. Okay, so even though we are running out of time, but definitely we'll give some scope to go for the question answer if anybody has any questions. So please feel free to ask, or you can also type a question into chat box as well. So in either way. So let's begin. If you have any question, please.
Hello. Yes. Can you hear me?
Yeah.
Yes.
Okay. I think it's very thought-provoking, very good. Thank you very much. It's excellent lecture. I can see that when your work is very in depth. Did you publish in paper on that? And the things you are just mentioning in future direction, this decentralized.
Oh yeah, this one not really. So it's kind of like the direction that we are pursuing at the moment. So this is actually the one that I'm showing here is coming from Bristol's university projects called Taurus. So this is where I basically propose an idea of like how we kind of like distributed or decentralize everything. So everything is kind of like on the edge. And then yeah, they basically got funded on that, and then I moved to Aberdeen. So yeah, so in terms of this, I'm actually not really involved anymore. But the part that I'm still pursuing is about like using or minimizing the size of the models that can be fit into the wearables, especially on the pruning technique, because the one that we did in the last slides is that we use quantization and also knowledge distillation. But now I'm thinking about like how if we use kind of like pruning on that as well, yeah, on the kind of like tiny ML. And the other direction that is also interesting here is that I don't think if anybody, I'm still new on this as well, that anybody hasn't really put into kind of like effort on understanding this, especially when you talk about robotics and edge devices, is neuromorphic computing. It's very suitable for this. The problem is that yeah, with the hype with the quantum computing, you people always go kind of in that direction. But when we talk about like the efficient deep learning models that only use like a fraction of power, then we need to go in this neuromorphic computing kind of like approach.
Okay, thank you.
Right. Is there any other question, please? Okay, so I have a question, Dr. Fardi. So that is, I have actually, a small multiple questions because you had, three different aspects of the presentation.
Yeah.
So one is maybe we can start with the very last one, the
Okay.
RSSI based location, detection, something. So as I can, recall and remember, the RSSI is very unstable, when you actually measure that. So how did you, what sort of techniques did you apply to stabilize this RSSI measure, or how did you collect this RSSI signals?
Yeah, I mean, in terms of like, it's true that the RSSI signal is very noisy, yeah. But yeah, that part is so the signal that we got is actually already kind of like filtered down by people from the engineering people. So it's rather clean compared to the actual signal. So there's some kind of a pre-processing on the wearable itself, yeah, to kind of filter down or clean down the RSSI signal. So yeah, I mean, I don't know. I mean, for the techniques itself. So it's
Right. So you basically utilize the process signals coming from the wearables itself, I think.
yes, yeah.
Right. Yeah, that makes sense. So yeah, I remember, when I was, in Samsung, so one of my groups working on this RSSI based, the proximity detections, and we showed and demonstrated that when, let's say, mobile approaching to you, and then RSSI signal strength is getting higher, and then when it's move away, so RSSI signal is
Yeah.
getting less. So I was wondering that. So this is one aspect. And regarding your that the first part of your lectures, so is very naive stuff, and because I don't know so much of those things. So how this signal, how you collected the signals there?
Which
Where are
one?
the signals? The very first part of your lectures, that is human robot interaction.
Okay.
So, for example, those signals, how did you collect those signals? What were the arrangement for that?
So yeah, this signals is actually coming from so this is so we have like the people tracker, let's just say people tracker. So it's basically a bunch of bunch of modalities. So you have the laser to detect the leg, and then you have the camera to detect the upper body, and it will kind of like combine them together, track them, and then it will create like a, yeah, because it's tracking, so it will create like a trajectory, yeah, over time, like the one here. And from this, then you basically you have like a kind of like a boundary area. So every time this line is inside of this, it's counted as one. Yeah. So then what you have is basically, yeah, so upper body like detection, and then you have the, yeah, predefined areas. When this line is kind of like in that area, it's counted as one. So then you at the end from that robot see is that it's a bunch of lines in terms of numbers. Yeah. So the signal is basically just numbers there, like the number of people in that area at that particular time.
So are those offline processing or real time?
It's
Offline,
a real time.
real time.
I mean,
Okay.
up to this point is a real time. Yeah, to get this point. I mean, actually, the whole thing is up to this point, it's a real time as well, because I mean,
Okay.
our not really real time. It's kind of like pseudo real time, because
Hmm.
otherwise it will kind of consume the energy. Yeah. So yeah, I mean, because of this data is a bit kind of like jaggy, and you have some missing data here and there. So we use Fourier transform to kind of like smooth it. So basically a filtering and smoothing process just to get, and the technique is just using Fourier transform because it's fast and it's simple.
So is there any numeric quantification or something to understand the successfulness of what you are planning as part of human robot interactions there, or
Yeah.
it is all about signal reconstruction time and
So yeah, I mean the signal reconstruction part is just one part. The whole point is that we want to optimize or maximize the human robot interaction. Uh, So basically, we just need to have like a schedule for the robot to do throughout the day. Yeah, it's kind of like which part that the robot needs to visit. Yeah, and yeah, basically it's a combination of optimization problem together with scheduling problem. Yeah, we use basically kind of like the position to decide where the robot needs to go. So at the end of the day, the metrics that we use. So this is kind of like, yeah. So you have all the data here, counting, combine them, and then create like a schedule. The metric that we use is here. Yeah. So basically the bottom part, we are saying like let's say that we claim that yeah, this model is a good to kind of like to maximize human robot interaction. But how do we show that? We show that by this percentage number. Yeah. So this percentage number here represents the number of interactions in that time. So the duration where the robot sees people over the total duration the robot spends in that place, if that makes sense. Yeah. So let's say 1 minute, within 10 minutes, robot visiting, I don't know, living room, for example. 6 minutes, it sees people. Yeah. Whereas like if you use kind of like random, it's only 4 minutes. Yeah. So we are basically using that to showcase that it's successful in terms of like maximizing its interaction. Yeah. So I mean, there's no actual interaction. I mean, there is like if they want to play with the robot, it's there. But the point is that we want to collect data that will be used to train at the actual human activity recognition. Yeah, that is based on the actual real world scenario, if that makes sense.
Yeah, right. Yeah. So it's great. Yeah. So thank you so much for this and explaining all this stuff. And is there any other questions anybody would like to ask? Okay, so I hope no other questions. So I am again thanking Dr. Ferdi Jovan for sharing your deep insights into how a robot can maximize this useful action and knowledge under this different kind of sort of constraint, and also explaining your healthcare platform for Parkinson disease, also collaborative robotic stuff. So all I guess useful, and this knowledge it's a very it seems fundamental and can be utilized in many domains. In fact, so with that, as a token appreciations, we'll be happy to present, certificate of appreciation. So which I will be sharing with you after the sessions. But still, I wanna, share, here just for the to see. So this is that one. Can you see
Oh yeah.
this?
Yes, nice.
Yeah, so I hope that you accept it. It's just a simple, piece of paper, or more about the digital papers, nothing else. Still, we are happy to present it to you. So
Thank
thank you
you.
for this. Yeah. So with that, I believe that we are here to an end. And thank you all once again for attending. And we hope to welcome you back at any future events that we'll be organizing as part of our VTS lecture series. And that's it. So, Ashraf, do you want to say anything?
No, thank you very much. I think this is very much appreciated that Jovan for the tremendous effort to complete this kind of lecture series, lecture today. And thank you very much, Riazul Islam, that you have organized and as a chair. And from us, I think it is very much appreciated that we are running this um, the lecture series. Hope to see you again in another lecture.
Okay, great. So maybe,
And
oh, okay, yeah.
thank you.
Okay, great. So thank you everyone again. So have good evening, and see you next time. Bye bye.
Bye bye. Thank you.